Analysis on disconnected nodes in wireless sensor networks. Abstract: in a wireless sensor network, existence of disconnected node is a common issue. Sensor devices, deployed under adverse environmental conditions, often lose their normal communication capability due to shrinkage of the communication radius. Numerous research works have corroborated this with hardware test results. In this paper we consider both temporary and persistent disconnections of sensor devices from the network. We present a probabilistic model that describes the probability of disconnection in terms of node density and communication radius. We also present simulation experiments that clearly differ networks with disconnected nodes from normally connected nodes. Our simulation experiments also report a 50% degradation the throughput and 28% extra energy depreciation with the occurrence of disconnected nodes in the network. The analysis and simulation experiments led us to enlist some open research issues in the concluding section. Keywords: wireless sensor network, disconnection, network simulator 3. Introduction. Wireless sensor networks, WSN, serve numerous applications needs for our day-to-day life. 1. To serve different applications, such as field monitoring, environmental data collection, forest fire detection, etc. Sensor devices are often deployed under environmental adverseness. Harsh environmental condition reduces the normal communication range of a sensor device too. Due to this reduction, the sensor node becomes disconnected from the network. However, this disconnection has no fixed time interval and other interesting properties as well. Several research works have proven the shrinkage of communication radius under poor environmental conditions with hardware test results. For example, authors in 3 has shown a 60% shrinkage in communication boundary with increasing temperature from 250C to 650C. Their experiments were carried out on Telos class motes, reported 8 dB RSSI loss at 65 degrees Celsius. Not only conventional communication protocols like IEEE 802.11 or IEEE 802.15.4 Zigbee suffer environmental adverseness, latest communication long-distance communication protocols like LoRaWAN, Sigfox etc. also exhibit disconnection and shrinkage of communication range under adverse environmental condition. For example, authors in created a setup with 915 MHz LoRa using Raspberry Pi and Dragino LoRa Shield hardware platform 5. Their outcome presented that the effect of humidity and temperature on the sensor device is far more detrimental than rainfall and snow. Additionally, they established a statistical CO relation between the humidity and Jayashri Sinha. Department of Computer Science Engineering. Bengal Institute of Technology and Management, BITM. Santiniketan, Duranda, Verbum WB, Pin, 731236. Temperature of inside and outside of an experimental device. In another similar approach, authors tested the propagation of 433 MHz LoRaWAN under rubber tree forest area. The results of this study also reported a significant degradation in RSSI with increasing forest density and other environmental issues. 6. Since shrinkage of the communication range is a common phenomenon for both conventional and modern communication protocols, disconnections of the devices from the network also becomes an inevitable issue. Moreover, primitive network management techniques like rate adaptation and others do not provide solution to these kinds of problems. 7. With the intention to study the properties and effects of such disconnection, we organize the remaining parts of the paper as follows. SEC-3 discusses about some common properties of disconnected nodes. Here, we present a probabilistic model that analyzes the probability of disconnection. SEC-4 presents simulation results which explains the effects of disconnected nodes in the network. In accordance, we enlist some open research issues in the concluding SEC-V. 2 properties of disconnection. As a sensor device experiences external environmental hazards, its communication radius shrinks and it becomes disconnected from the network. However, this disconnection has several interesting properties to discuss. A probability of disconnection. The disconnection of a node from the network depends on the shrinkage of the communication radius. We can show that the probability of disconnection depends on the average density of deployment aid. Theorem 1, the probability of disconnection of a node from the network depends on the deployment density. Proof: let us consider a network on k nodes deployed in A area with node density, k/A. Now if the communication radius of a node shrinks to R unit distance, there will exist nodes in the PR2 region. Now, can be formulated as shown in. Therefore, the probability Px equals 0, that there will be no nodes in the PR2 region will be. Putting the values of and x we get. Equation 1 establishes the correlation between node density and shrinkage of communication radius. If we consider that at a particular time instance communication radius, r, remains constant, Px equals 0 becomes directly proportional to node density, k/A. This proves the statement of the theorem. B. Duration of disconnection. As the disconnection depends on environmental adverseness, the time duration of such disconnection is purely random in nature. 10. If a node remains disconnected and connected for t_d and t_a unit time durations, and the outcome of the node is traced for .t time units, then the length throughout, th, becomes. Here pt is the average packet disbursement rate, in unit time, with packet size. Corollary, link throughput is directly proportional to connected time interval. Proof: we use equation 2 to prove our notion. Where is the observation interval that can be considered as constant? Similarly, and can also be considered to be constants that remains unchanged during simulations as well. Therefore, additionally, sensor devices can automatically re-establish their connectivity with the appearance of favorable weather condition. Therefore, the ratio between t_d and t_a is stochastic nature. In the simulation, we randomize the CO relation and observe the variation of throughput in figure 1. 3. Performance analysis. To analyze the effects of disconnected node and disconnection interval, we simulated several network scenarios with the following simulation parameters. A. Simulation parameters. We use Network Simulator 3, NS3, to simulate disconnected network conditions. 11. Although NS3 is a discrete event simulator, yet continuous submission of task keeps the clock active throughout the simulation period. Thus, we track the time and schedule the activity of different nodes on different times, which institutively expresses that link throughput is directly proportional to the connected time interval. B. Results. In our first experiment we deploy 10-18 nodes over 300 m x 300 m terrain. We discontinue the normal transmission ability of the node by impairing default send methods. We schedule this disconnection, t_d, for a pseudo time interval for selected nodes. Figure 1 shows the variation in the collected throughput in different time intervals. We observe a sharp decrease in throughput in the network with 18 nodes topology during 200s to 400s observation. INTR eval, occurrence of multiple disconnected nodes in a same reason can be considered as the main reason behind this 12. In our second experiment we gradually increase the percentage of disconnected nodes in the network. The results in figure 2 shows that with the increase of disconnected nodes from 0% to 30%, a degradation in throughput observed is almost 50% in 20 node topologies. In accordance we deploy 20 nodes in 400 m x 400 m area uniform randomly. We observe the throughput with AODV and OLSR routing protocols with default setups presented in NS3. The resulting figure exhibits that in all test cases OLSR outperformed AODV routing protocol. For example, we observe a 28% extra network throughput with OLSR, compared to AODV, having 30% misbehaving nodes in the network. The results of this experiment also corroborates the findings of 1314.s. In our final simulation we deploy 20 modes in 400 m x 400 m deployment area with initial energy budget 100J, total We track energy per received packet and plot figure 4. We observe a significant decrement, 30% approximate, in energy utilization with 30% disconnected node. For conclusion. With the analysis and simulation results we have corroborated the existence of disconnected nodes. We feel the discussion is essential since it is an inevitable issue, mostly in networks with outdoor deployment. Several techniques have been proposed to alleviate the effects of this problem. However, there are several issues which can be considered future work. Coexistence of disconnected and connected node creates disconnected topological segments which needs to be connected with minimum latency paths. Therefore, an improved routing protocol which accounts disconnected nodes separately can be an interesting future work. Almost all recovery mechanisms focus on distributed recovery or self-detection principle. However, they overlook security concerns like node hijack or malicious node insertion etc. 1516. Therefore, a recovery mechanism with security concerns will improve both performance and robustness of the network.